Welcome to the video. This is part of my series where I break down the core ideas behind systems, databases, and the runtimes our code runs on. Today we're looking at garbage collection, how a program automatically figures out which memory is still in use and which can be reclaimed. We'll start from the single idea behind every collector and build all the way up to how Java, Go, and Python do it in production. Let's get into it. Every program you write allocates memory. You create an object, a list, a string, and somewhere, that's a chunk of memory on the heap. The question nobody likes to think about is, who frees it? In languages like C, you free it yourself. Forget to, and you leak memory. Free it twice, or free it too early, and you get crashes and security bugs. Garbage collection is the alternative. The runtime watches your objects, figures out which ones you can still reach, and quietly reclaims the rest. The whole field, going back to McCarthy's 1960 Lisp paper, is built on one deceptively simple idea. An object is still alive if you can reach it. Everything else is garbage. So what does reachable actually mean? It starts with the roots. Roots are the references the program can touch directly right now. Local variables on the stack, global variables, CPU registers. Anything the running code is holding onto. From the roots, you follow references. A root points to an object. That object points to another object. You keep following the arrows. Every object you can reach by walking those arrows is alive. And here's the key insight. If an object can't be reached from any root, it doesn't matter what points to it. Even if 100 other objects reference it, if none of them are reachable either, the whole group is dead. It's just floating, disconnected from the program. That single rule, reachable from a root, is what every tracing collector is built on. There are two fundamental ways to find the garbage. The first is reference counting. The idea is simple. Every object keeps a counter of how many references point to it. Assign a reference, the count goes up. Drop a reference, the count goes down. The moment the count hits 0, nobody's pointing at the object, so you free it immediately. This is nice because reclamation is instant and the work is spread out. There's no big pause. Python uses this as its primary mechanism. But reference counting has a fatal flaw: cycles. Imagine object A points to B, and B points back to A. Now drop every outside reference to them. Their counts are still 1, because they point at each other. Neither ever hits 0. They're unreachable from any root, but reference counting will never free them. That's a leak. This is exactly why pure reference counting isn't enough on its own. The second approach is tracing, and the classic form is mark and sweep. Instead of counting references as they change, tracing periodically asks one question. Starting from the roots, what can I actually reach? The mark phase walks the object graph from the roots and marks every object it visits as alive. The sweep phase then goes through all of memory and reclaims anything that wasn't marked. Notice what this does to the cycle problem. Our A and B cycle, with no path from any root, simply never gets marked. The mark phase never visits it. So the sweep phase reclaims both. Tracing collectors don't care about cycles at all. They only care about reachability. One practical note: walking the graph recursively would blow the stack on a deep object graph. So real collectors use an explicit work list instead of recursion. Once you commit to tracing, there are a few ways to actually do it, and they trade off against each other. Plain mark sweep marks the live objects and frees the rest in place. Simple, but it leaves gaps. The free memory gets fragmented. Copying collectors fix fragmentation by splitting the heap in two halves. They copy all the live objects from one half into the other, tightly packed, and then the old half is entirely free. The cost is that you only ever use half your heap at a time. Mark compact is a middle ground. Mark the live objects, then slide them together to one end so the free space is one contiguous block. No wasted half, but moving objects means you have to fix up all the pointers to them. And then there's the generational hypothesis, the observation that most objects die young. A few survive a long time, but the vast majority become garbage almost immediately. So instead of scanning the whole heap every time, you focus collection on the young objects, where most of the garbage is. That one observation is behind a huge amount of real-world GC performance. The toy version stops the whole program while it marks and sweeps. Modern collectors do most of that work concurrently while your application keeps running. Let's look at 3 real ones. Go uses a tricolor concurrent mark and sweep. Tricolor is the trick that makes concurrent marking safe. Objects are white, not yet visited, gray, visited, but their children aren't, or black, fully processed. The collector works on the gray set until it's empty. To stay correct while the program is mutating pointers underneath it, Go uses write barriers that catch new references being created during the mark. Notably, Go does not compact memory. That keeps its barriers simpler, since pointers never move, but it relies on a size class allocator to keep fragmentation under control. And for a long time, Go skipped generational collection too, because the write barrier overhead wasn't worth it for typical Go workloads. Java gives you a menu of collectors. 2 worth knowing are G1 and ZGC. G1, garbage first, splits the heap into many small regions and is generational. Its trick is that it estimates which regions have the most garbage and collects those first, which is where the name comes from. It compacts as it goes, so it avoids fragmentation and gets fast bump pointer allocation. ZGC is built for one thing: extremely short pauses, sub-millisecond, even on huge heaps. Its signature idea is colored pointers. It stores GC metadata, like mark and remap state, directly inside the bits of the 64-bit pointer. Every time the program loads a pointer, a load barrier checks those bits and fixes things up on the fly. That load barrier on every pointer read is the price ZGC pays to almost never stop your application. Both are just different engineering answers to the same question. How do we trace and reclaim while pausing the program as little as possible? Python rounds out the picture because it combines both families. Its primary mechanism is reference counting, instant, spread-out reclamation. But remember the cycle problem? To handle that, Python adds a supplementary cyclic garbage collector that runs a tracing pass to catch the cycle's reference counting can't. And that's really the whole story. Every modern collector maps back to the 2 families: reference counting and tracing. Tracing dominates managed server runtimes. Generational collection shows up almost everywhere. Compaction is a genuine design fork. Java compacts, Go doesn't. And colored pointers are just a modern take on stashing GC metadata in the pointer itself. But under all of it is McCarthy's original 1960 insight: unchanged. An object is alive if you can reach it from a root. Everything since then, concurrency, generations, colored pointers, is an engineering refinement of that one idea.